Welcome everyone to this webinar entitled Surface Power Facilities, Geothermal Energy to Electricity. This series is brought to you by the GEODE consortium, which is led by Project Interspace and the Society of Petroleum Engineers and is funded by the U.S. Department of Energy's Geothermal Technologies Office. My name is Deanna Morrison. I'm your facilitator today. It is now my pleasure to welcome our moderator, Luca Zotto. Luca is the sitting chairperson of ETIP Geothermal, a global geothermal energy and consultancy company founded in 1987 in Pisa. Luca holds an MBA in energy from the Eni Corporate University and an MSc in energy engineering from Politecnico di Milano in Italy. A lifetime geothermal professional, Lucas started his career with Exergy, an ORC binary plants manufacturer, where over 10 years he became an expert in geothermal power plant technologies. In recent years, Luca has advised on geothermal projects throughout the world regarding resource assessment, drilling, engineering and construction of brownfield and greenfield geothermal projects, mineral extraction projects, and feasibility studies. In addition to authoring and co-authoring several scientific papers and books, he engages actively in knowledge sharing and capacity building through speaking at major conferences throughout the world and leading geothermal workshops in Europe, Asia, and Africa. I'll turn it over to you now, Luca.
Thank you, Diana. And it's my pleasure to welcome on stage Stefano. Stefano Orlando is the head of engineering for STEAM, and he holds a MSc in chemical engineering that he took at the University of Pisa. And Stefano, since 2015, has been involved in design and implementation of geothermal steam fields and power plants worldwide. He has a deep expertise in process engineering, and he has managed every step of a geothermal design project, from the feasibility study through the plant design and optimization, gathering system design, and even field commissioning activities across a range of low and high enthalpy projects. He has held technical leadership roles on landmark geothermal developments such as Olkaria and Menengai in Kenya, including both the power plant and the gathering systems, and Tiwi in the Philippines, and also he commissioned several plants around the world. So Stefano, welcome to this webinar.
Hi, thank you, Luca. Thank you very much.
Great. So let me just enter a bit into the goals of today's webinar. So first of all, we would like to understand the fundamental characteristics of the geothermal fluid handling, and what are the main characteristics of these fluids. As a second point, we would like to understand the geothermal power generation technologies and their respective applications. As a third one, we'd like to share with you some sizing and design considerations for surface plants for the optimal investment and performance. And finally, we would like to foresee and mitigate inherent risks in fluid chemistries. How will we do that? We will have a discussion structured into 6 sections. The first one will be dealing with what happens when the fluid reaches the surface. The second one will be on the technology for the surface facilities, and then just after that, how to design and optimize a surface facility. Then we will dig a bit into the fluids, the geothermal fluids, and then we will share some case studies, and in the end, we'll try to discuss a bit about how geothermal and oil and gas are connected also on the surface facilities point of view. I'd like to ask all the attendants to share their questions live. So you've already been instructed to use the Q&A button. We will track your questions and try to answer during the presentation, and then also we will leave some room at the end of it to discuss a bit more. So let's start with section 1, Stefano. So we all know that the geothermal project, similarly to the oil and gas industry, has a very long de-risking and upstream exploration and development phase. So we start with some resource assessment, we go through surface exploration, then we get into the feasibility studies with a deep exploration, And in the end, we have some wells that are tested and ready to produce. So at that point, we need to take our fluid, and depending on its state, we may need to separate it, and we may need to process it somehow at surface. You have started up and commissioned several 100 megawatts of geothermal wells and gathering systems. So how would you describe the process at the surface?
Yes, thank you, Luca. So what we need to understand is that it's water, right? But when it reaches the surface, typically it's a two-phase. So we have both steam and liquid. This liquid usually is called brine because it has a certain salinity. And I mean, to be used, we need to separate these two phases. So the steam from the brine. So as we can see in this picture, we have the well going to a separator that is equipment very, I would say, also common in the oil and gas field, right? And where we separate the steam and the brine. Now, what we do with the steam and with the brine, it is something that depends very deeply with the technology that we are going to see later, right? In terms of how I'm going to exploit and harness whatever the resource from the earth, right? So, and as you can see here, I can do several things actually. The most important thing to understand is that we can have wells that produce more steam than brine, or wells that can produce more brine than steam. So, I mean, each well has its history and his behavior, and it is very fundamental to understand this behavior to better and harness this let's say skills from these wells. Okay, so I would say that there are, I mean, the most important thing to understand is that for a geothermal plant, and when I say geothermal plants, I mean from the wellhead of production to the injection wellhead, we have, let's say, two main parts. The gathering system, that is the system that we use to go from the production wellhead to the power plant, and also from the power plant to the injection wells, and also from the production, let's say, wells somehow to the injection well. So what we need here is to understand that the gathering system is composed of several equipment, like separators. Then we can have a water tank. We can have, of course, rock mufflers. Then we have pumps. And then, of course, valves and all the instruments that, I mean, are used also in the oil and gas. Then we have the power plants, and the power plant is something that is related with the technology. Anyway, we are talking about, of course, turbine, generators, gas removal systems, cooling towers, or also that can be, let's say, wet and dry. Then we will see later that. And then, of course, generator to, of course, to transform the mechanical energy to electrical energy. In the pictures, as you can see, we can find, for example, separators that are top one and the bottom one, while the left picture is a rock muffler that is a very typical equipment of a geothermal field, where the steam is sent inside a chamber where we have rocks on top that allows the to, let's say, lower down the noise of this emission. So keeping that in mind, I think that we can see which kind of technology and cycle we can have with the geothermal resource. So let's say that moving forward, we can say that depending on the reservoir characteristics, we can have a dry steam that will lead us to a direct cycle, right? So it means that we will have the steam going directly to the turbine.
Yep.
Yep. Perfect. Thank you. Direct to the turbine, and then it will be in the turbine. Of course, the steam will lower the pressure, transform its internal energy to mechanical energy, and during this transformation, it will condense partially. So it will go to a condenser. Now, in the condenser, we will have a system to remove the non-condensable gases, because what it is good to know in geothermal is that we have to deal with steam that is not pure. but it is a steam with non-condensable gases. These non-condensable gases come directly from the earth. So we are talking about like carbon dioxide, hydrogen sulfide, some chloride acid, something like that. And of course, when we have to deal with this kind of resource, we need also to keep in mind how to remove them. Usually, as we said, in the condenser, we have a section that removes this kind of non-condensable gases. Then the condensed steam is sent to the cooling towers, and then in a, let's say, closed loop, the water is sent back to the condenser, and then the excess water, it is sent to the reinjection well. Of course, this is dry steam, so we only have steam coming from the well. But if we have a well that is producing a two-phase, as I said before, that is the main, let's say, the typical well that we can find around the world. Let's say that we have the separator, as we were saying, and now we have the steam going to the, let's say, steam turbine to produce energy, and it will follow the same cycle as the direct cycle. And then the brine can be or injected, or as we will see later, it can be also, let's say, used to produce more energy, or maybe to give heat for direct uses, right? So like pasteurization, drying, and something like that. So it is very important to understand later also the brine chemistry that will lead to some issues to the operation, right, of this kind of plants. Then if we move forward, we can say that the next one would be a double flash. Double flash means that we have a double separator, meaning that after the first separator, the steam is still sent to the steam turbine plant, right? And the brine has still enough energy to be flushed again to produce other steam. And this steam will, let's say, or go to the same turbine with the low stage, in the low stage turbine, or maybe there will be a different turbine producing more energy. Then with the residual brine, again, we can or directly inject to the wells, or we can use it again. Anyway, this kind of operation or this kind of choices are very strictly dependent on the brine chemistry or the resource characteristics. So you cannot say a priori if that kind of technology can apply to your resource. You need to understand the behavior and how it's going to, which kind of issue you could have along the way. And then finally, I think that we can discuss about the last technology that we can implement in the in the geothermal for producing energy. That is the
Binary.
URC, the binary
Yes.
system,
So
right?
yeah, the binary, let's say, I wanted to ask you this question because we have talked about the steam turbines until now, and I would say that around 80% of the installed power plants around the world are equipped with the steam turbines. But there is a growing content of another technology that is the binary technology, and it's called binary because we have two fluids in the cycle. So can you talk a bit about that?
Yeah, for sure. We should have also a scheme for that. So let's say that the binary systems are system where we have the geothermal fluid. Can you move to the next one? Sorry, Luca.
No, I think it's missing.
Ah, perfect.
Yeah, so so we can stay on this, yes.
Okay, perfect. So let's say that we have the geothermal fluid is sent to heat exchangers to exchange the heat with the binary fluid that can be an hydrocarbon or can be a refrigerant. It depends now on the regulation and on other, let's say, aspects. And this fluid has a low boiling temperature and pressure, so it can be evaporated through this heat, and then it will drive a turbine to produce electricity, sorry. Then it will be condensed inside or a water-cooled condenser using wet cooling towers, or through, let's say, what are called air-cooled condenser or dry cooling towers that are for equipment that uses equipment yet that use air to cool down without the involvement of water. And this is particularly interesting, especially if we are in let's say in location where the water is not abundant, or if the steam coming from the reservoir is not enough to let's say to supply the makeup water for the cooling tower. So having that in mind, I think that we can see what is the kind of layout surface that we can have in a gathering system, right? If we are talking about a high enthalpy or a low enthalpy plants. So let's say that a high enthalpy plants usually involves big pipelines, right? We try to gather all the steam to go to a central power plant to produce this energy, right? In as we said, in a steam plant, in a steam condensing plant. Or if we have, for example, an ORC or a binary system, ORC, sorry, is organic ranking cycle. So it's a kind of a binary because that uses as a binary fluid an organic fluid. We can have maybe some more compacted layouts. Luca, can we go to the next one? Yeah, so as I was saying here, for example, we have an example of on the right, we have an example of a Las Pailas geothermal plant where we have a steam condensing plant. I think it works at around 5.5 bar at the inlet of the turbine. And as you can see, we have 3 production pad 1, 8, and 3, and the steam is collected to the power plant where it produces the steam, the energy. Now we have then the reinjection pad that are pad 6 and pad 4, and where we reinject both the cold and the hot water. So let's say that this is just to explain that the resource also affects the layout of the gathering system, right? And of course, if I have a high enthalpy resource, I will need maybe less gathering system or less wells per power plants to produce the same amount of energy. But generally speaking, it is not something that can be said a priori, but we need always to know the fluid characteristics.
Yeah.
So
sure.
I
this
think
is
we
another
also have
example,
another.
I think.
Yeah.
Yeah.
Yeah. This is why we do single flash power plant in Indonesia. As you can see, it's we are talking about as you can see here that there is the two-phase stage, the pipelines taking the two-phase flow to the separator. Then we have the steam pipelines, the powerhouse down there with a lot of pipings. And what we need to understand is that we are always dealing with hot fluid. So it is more of attention for us, the stress analysis and the routing of the pipelines, right? So it is very important to understand that we cannot just go straight from allocation from point A to point B, but we need to keep in mind that since the fluids are hot, the pipe will expand. So we need to also give flexibility to the pipes to avoid any failure of the piping itself. And as you can see here, we have several horizontal expansion loops. So in case you were asking why we have all these expansion, this loop. So moving forward, I would say that what determines the design in a geothermal plant, for sure, is the temperature, the pressure, the flow, and the chemistry. So we usually understand what is the heat, the energy capacity that the resource has, and then we try to optimize the exploitation, if we can say exploitation, of this resource. Of course, sometimes it's better to call it cultivation because it is something that we want to keep in time. So it is also important to keep in mind that we don't have to exaggerate with the flow rates and whatever, because we need to save the resource. So if we want to keep it last long, we need to understand how to manage that. Of course, for doing that, there are several techniques, software, and let's say forecasting application.
Yeah, and I
Don't
think
know, Luca, if you want to,
Yeah, I think you clarified quite well what happens at the production side and how the characteristics of the fluid affect the design from the point of view of the gathering system. I think also the reinjection is an important part for the reason that you just mentioned. So it's important to target also the reinjection in the right area of the reservoir,
you're right.
to keep the reservoir under pressure, to keep the fluid present in the reservoir. Obviously, we don't want to just exploit it for a few years and then lose it. That's what happened, for example, in the geysers in the 60s, 70s of last century. Luckily, then we found a good way to reinject, and now I think that it's very rare with modern technologies that we deplete a reservoir in a less than 30, 40 years. I would say that all the business plans are based on 20, 25, 30 years for the power plant, but maybe up to 50 years for some special reservoirs, right?
If you keep in mind Laderello has been running for the last 100 years plus, so that is a very clear example of how to manage the reservoir. Anyway, whatever you are saying is correct, and what I can say is that we, as a surface engineers, we just hope that whoever came before us did a good job and give us all the, instruction and all the data to then, of course, design or whatever it is on the surface. So, yeah, I mean, at the injection well, as you said, it is very important. And I would say that is more or less the heart of a geothermal plant, because without reinjection, we cannot produce anything because we can have issues. So, of course, the plant, the production plant is very important, and also the production wells are very important. But sometimes their injection wells are underestimated and are actually very important, because without them, we cannot reinject, and without an injection, we cannot have production.
Great. So let's say we talked a bit about the characteristics of the fluid in terms of physical characteristics and also chemical characteristics. So I think we can now get a bit more into how to choose the right technology. You mentioned the different possibilities of single flash steam turbines, double flash steam turbines, binary systems. So how do you choose? I mean, is there any typical applicability range for these technologies?
Yeah, I mean, for sure, to have enough steam at the wellhead, we need to have a reservoir with at least a minimum temperature, right? Or enthalpy, right? Because usually temperature and enthalpy are strictly related. So we can say that a cutoff, it could be that if you have more or less around 200 degrees Celsius in the reservoir, maybe you can think about a steam condensing plant. If you have something below, then for sure you need to go for an ORC. I mean, but then, as we will see later, there are cases where even though you have a very good quality reserves in terms of enthalpy and flow, maybe the ORC is still the best solution because of other aspects, right? So let's say that, at first sight, if you see a high temperature, you should go for a steam turbine plant.
A steam turbine, sure.
Yes.
But then there are also other characteristics, and you already mentioned the NCG content, so the non-condensable gases content. So how do you deal with non-condensable gases? I mean, let's talk about that in a conventional way, and also from the point of view of the most modern technologies, and how, let's say, where the market is going also.
Yeah, for sure. As I said, non-condensable gases are part of geothermal, right? So we cannot avoid them. They're there, and we have to accept that. Whatever we can do is to try to understand how to deal with them. So in the history, several attempts of different gas removal systems were tried. And we say that, I mean, it depends, no, case by case, what we can do. If we want to go for a steam turbine plant because the enthalpy is still very good, maybe we say, okay, we go for that technology, and then we see that to extract these NCGs from the condenser, we need a lot of loads, parasitic loads that is not very convenient. So maybe it's better to find a way to remove before. And then there was a kind of reboiler system to remove this one. And I mean, it can be very complicated. And this could maybe lead to say, okay, let me use an ORC. Because when I have an ORC, I will never go under vacuum conditions. So the NCGs will be always under pressure. So when I have to remove them, I already have some pressure that I can use. And usually, I would say lately, the zero emission or the full injection is a strategy that is taking place, and it is something that can be realized very easily for sure with the binary system, because as I was saying, we already have a fluid that is under pressure. And as we mentioned, we have the steam, right, that is passing through a heat exchanger. So we will have maybe, I don't know, half a bar of pressure drop inside the evaporator, that is called evaporator because it's evaporating the binary fluid, but it's condensing the steam. So at the end of the condensation of the steam, I will have the a vapor phase or a gas phase where I have a lot of NCGs and very small quantities of water, and it will be under pressure. So it will be easier to send to a compressor, right, to compress it, to reinject it fully. Or if we can say that there are, let's say, other condition that we need to keep in mind, that for sure the steam turbine can give you a very high, let's say, output, right, Luca? So, I mean, it's easier to find power plants with, I don't know, 80. I think the biggest one should be 180, something like that, or one in New Zealand. It is a massive, a very huge turbine. And it is usually, of course, a steam condensing turbine. Usually with the ORC, we cannot have this kind of output with only one equipment. And you know better, right, Luca? Because I mean, you started as an OR in that field. But I
believe that the biggest ORC currently in installation is in the range of 50 megawatts per turbine. So it's let's say around 30-40% less than a single steam turbine.
Yeah, for sure. Yeah. So I mean, when we discuss about ORC, we have for sure, let's say, to have the same output, we need, let's say, more turbines or more equipment. But for sure, we also have maybe more flexibility. Why? Because to have a good quality resource, let's say good quality, but I don't want to be, let's say, I don't want to classify in good and not good resource, right? Just resource that can allow you to produce more. I mean, it's easier with the steam condensing turbine, but with the ORC, it's more flexible because we can install an ORC also when the resource is not so, let's say, with the high temperature and high enthalpy. In fact, what happened in Italy when geothermal was discovered and started to be really studied, they found in Larderello that there was only the dry steam, right? So they were always looking for high enthalpy resource. When they found, for example, in the south of Italy or also in Tuscany, some resource that was not so high in enthalpy, they discarded it, like it was not good. And in time, we understood, I mean, more worldwide, that also that heat is important, right? Especially because it's still a renewable energy and it's coming from the earth, and it can give us a lot of chances in terms of electricity or at least a heat, right?
Yeah, I would say that the steam turbine can exploit the lowest hanging fruit, that is the very high enthalpy geothermal fluid. But little by little, we are shifting towards binaries just because we are getting the other fruits that are less, let's say, less reachable because they have a medium enthalpy. And I would say, for the example of Turkey, has been very, very good in the last decade, or let's say last 15 years. They have developed around 1.8 gigawatt, and that's basically on medium enthalpy and binary systems. So let's say when you say it's more flexible, I would say it's because it can exploit really any kind of enthalpy from 100 something degrees
Sure.
to the highest ones. And staying on let's say on the resource. Later, we will get a bit more into the brine chemistry, but at a high level, how does the chemistry influence the choice of the technology? So, for example, you mentioned the double flash technology compared to the single flash that would have some issues with silica, for example.
I mean, yeah, in fact, that is very important. We need to realize what we have to deal with, right? And as we mentioned earlier, the brine chemistry is something very important. Let's say, the biggest enemy in geothermal are for sure the silica, the calcite, and the sulfides. Those are the three, let's say, biggest enemy for a geothermal operator, right? Because with temperature dropping, we can have a silica deposition, also with the flushing. So it is very important to understand what to do and how to do it. And of course, the brine chemistry is something that is that drives your final decision. Because, for example, let's say that I do calculation, I find that my optimization is to have a separator working at, I don't know, 6 bar. And with that one, I will have the best efficiency possible from the reservoir. Now I understand that I discovered that at 6 bar, I will have full deposition of silica. So I have to deal with that. So I cannot go down to 6 bar, but need to increase the pressure, right? So to avoid this scaling. So that means that also the brine chemistry affects, and not a little, but I would say massively, the choosing of the right technology.
Yeah, great. So I think there are also some other constraints that would favor some technologies over others. You mentioned, for example, water availability for the steam turbines, that you generally try to go for a water cooling, and that you need to have the right, let's say, the right characteristics. But in some cases, there are also requirements of zero emission, as you mentioned, where the binary is favored. So let's get into a couple of examples of cases where the binary was almost an obliged choice.
Yeah. In fact, for example, Cerro Pabellón, that is in Chile, it's a plant from Enel, an Italian developer company in geothermal, and they used two Larderello, right? As I was saying before, and also a Mount Amiata, where the enthalpy is very high. So when they had this opportunity in Chile, they said, okay, let's go for, let me call it traditional, but let's say a steam turbine, a condensing steam turbine plant, right? Then the plant is at, I think, at 4,500 meters above sea level. So it means that usually it's very cold. And in the cooling tower, we can have issues of icing, freezing of the water, meaning that I can have issue with the running of the power plant. So someone in Enel had the idea of saying, okay, I will maybe produce a little less, but at least I will produce always. I will always be producing, right? So let's put an ORC instead of a steam condensing turbine plant. And for this reason, now in Cerro Pabellón, we can find a binary system instead of a steam condensing plant. Yeah, because also the other point was that the low atmospheric pressure was not helping with the coming back of the water from the cooling tower. So other pumps should have been utilized, increasing the parasitic loads. And at the end of the day, maybe the parasitic loads would have been the same of the ONRC with the risk of not working 360 days per year.
Yeah, if
And I
I
think
remember
that,
well, if I remember well, there were also some collateral issues that brought to the choice of the binary, and there are 3 units installed in the area of Cerro Pabellon, and one of the issues was that even for the civil works, foundations for huge steam turbines were not, let's say, constructable because the concrete would not dry in a sufficient time due to the environmental conditions. So that was a huge issue that brought to the selection of smaller units, such as the binary ones. Another point was that the plant had to be automated because nobody could live at that altitude due to the Chilean regulation. So I think that's a good example. And I think in the US, there are some climates that are surely not as extreme
yeah,
as the one in Cerro Pabellon, but surely can get to very cold conditions, right?
yes, as you can see here for Casa Diablo in California, the technology is still a binary ORC. And I would say that we can find as a similarity the fact that we are in elevation and that the temperature during winter can go very low, and also the atmospheric pressure is not so high. So maybe it is better to, of course, to use the binary technology compared to the steam plant.
Yeah.
So
So
I
we
would,
have a question on this point, on the choice of let's say the ORC modules and the turbines. So the question is, let's say that we have a 40 megawatt geothermal resource, 40 megawatt potential, and you need to choose at a, let's say, medium high enthalpy, so 170 Celsius. You have to choose how many ORC units to use. So let me start the answer, and then I ask you to contribute. I would say that the market trend that we see now is to go for big units. The example of the project that is being built at the moment in Utah, where every single unit is in the range of 50 megawatt net, says that the market is going into bigger units. But traditionally, we've always seen smaller units like 10, 15, 20 megawatt. And that was also due to some kind of staged development. How do you think that you should choose among different sizes?
I would say, flexibility could be an aspect you can have in mind, right? I mean, if in steam turbine, efficiency increases with the size. A big size has a very high efficiency. But in ORC, what we saw is that more or less, let's say more or less, the efficiency is not too different between a small size to a big size, at least. We always are more or less in that range. So I would say that it depends on what you want and what would you like to have. For sure, if you have more units, for sure you are more flexible, because if you have an issue only on one unit, you can keep producing. Of course, this one will increase the capex, also the OPEX.
Yeah, sure.
It depends, I would say. It depends, but if I don't mind that I can have a shutdown because of a problem, then maybe I will go for the biggest possible. If not, maybe I could go on a, how can I call that? A proven technology in terms of size in the market with a background, right? So that we have case history, something like that, and data that says that the turbine can work for, I don't know, 10 years, 15 years at least, without any major issue. So I would go for a market scouting to understand that.
Yeah, I agree. Great. So let's get a bit more into the design of the surface plant, so the power plant and the gathering system. So let's say we now know the resource. We have chosen a certain technology. So how do we design and optimize the plant?
Yeah, now that is very funny because geothermal has also to do with the environmental, right? Environment, but I'm not talking about in terms of emission that is everywhere. I mean, whatever, but we don't have always a flat surface. So we need to understand what to inject, how to inject, because as I said before, injection is very important. So sometimes the optimization of the gathering system can be just to have clusters of separators or just a separator per well, having the production well at the higher elevation than the injection well. But that is something that should be the optimum. But of course, we cannot decide which elevation has the production well. It is the reservoir that will tell us which one is the injection and which one is the production well. So it is very important to understand that, because when you do then the calculation, for the heat mass balance, you need to understand how to do things, because the most important aspects are what I'm going to provide at the inlet of the power plant, and then how the power plant will work with the characteristics I'm providing you. So it's very important for us to understand that, because if I make a mistake in my calculation, maybe I don't know, I underestimate something, and then I can have, of course, as in all the industry, issues, right? Especially I will not produce as expected.
Yeah.
So
Yeah. So let's say, first of all, know your resource. Second, know your constraints. Let's say.
yeah, for sure.
So I remember a case where we were inquired by a client that asked us, please help me procure the surface facility. And then you and I sat at the table and said, okay, let's look into the input data. And we understood that the client had no clarity on the input data. So let's say the first thing is to understand what will be coming out of your wells. Let's say design a closed, good heat and mass balance, but also, as you said, take into account all the constraints. One of the constraints may be also the availability of water. So how do you choose how to design the cooling system?
I mean, for example, let's say if I have enough steam and I'm not using the brine, I can decide to use the steam itself once it's condensed to as a makeup water for cooling tower. So I can have ORC or steam condensing plant, right, with cooling tower. Of course, as if I am allowed to do that in terms of, as we saw before, temperature and pressure, right? If I can use that, for sure I will go for cooling tower, because the parasitic loads are for sure less than a dry system. Or for example, if I have an ORC, a binary system, I can also decide to go for a water-cooled condenser if I have, for example, a disposal, a source of water like a river where I can take water, or maybe, I don't know, shallow wells that I can use to get water. I mean, then it depends very strictly on the regulation that I have in that location, right? And then, of course, if I don't have enough steam and I want to also exploit the brine, of course, I need to go for the dry solution, because this way I for sure have no issue. Then lately, I think that a new technology is taking place, at least potentially, that are the ECC, evaporative cooling condenser, that are something like the dry system, but with some water sprayed on top of the pipes to enhance the let's say the heat exchange with the air.
So
Of
let's say
course,
you have
this one will
better performance than the air cooled, but you have a lower
less water.
water
Yes.
consumption than the
So,
water cooled. Yeah.
I mean, it will be something, that can also help you maybe with compared to the dry system with the hot season, right? Because the dry system, as all the systems, suffers the seasonality, and the dry system more than the wet system is very affected by the hot temperature of the environment.
Yeah.
Then of course you need. Yeah, please.
Yeah, no, there are also other parasitics
Yeah, for sure.
additional to the cooling system, and I think we have obviously the well pumps, but let's say it's I'm not sure we should consider them as surface facilities as they are inside the well. But I think that one message that we want to bring is that the optimization should not just be on the size of the turbine, but it should be on the net power, right? So what is the impact of the other auxiliary loads?
Yeah, and that is very funny, especially for the binary system, right? Because if I change the fluid, I can have maybe a greater gross power, but then a lower net power. So because the parasitic are so high, and all of the gross I produce, I will spend. If I produce more, I will spend for the parasitic. So yeah, it's very important to deal in an efficient manner with the resource.
And I think,
Mhm.
sorry, and I think that you mentioned the ambient conditions and the varying ambient conditions. So I think there are two flexibility needs in a geothermal power plant. One is towards the conditions of the environment, especially regarding the weather over the year, and the other is a flexibility on the resource, because we designed the power plant with the wells tested for maybe 1 month, if we are lucky, or maybe 3 days if we're not lucky. But then this plant should produce as much as possible for 30 years. So how do we deal with this flexibility need?
I mean, if I can make a joke, we pray the gods, right? Of the geothermal, that everything goes well. No, I mean, it is something, as we said earlier, right? We have now systems and software and application that can help us in forecasting the behavior of the reservoir. So as we said, we have maybe a well that is tested for a month, and that is something that is very good, actually, because we can, as you said, we can have a well tested only for 3 days. So we can use these parameters to understand the behavior of the reservoir. But of course, as I said, it's something that is usually being done previously, and it is something that we should get as an input, right? You have to produce this one from this well, this one from this well, and this one from this well. I mean, or the well is capable of producing this and this and this. So I would say that, yeah, for sure, the flexibility and the efficiency should be the main topics that we always keep in mind, because it depends. I mean, if I want to have a lot of flexibility, I have also to pay more, right? And as I always go around saying, geothermal is poor compared to oil and gas. So sometimes it is a matter of understanding if it is better to spend more now to spend less later, or spend less now starting, right? Start the plan, start to earn some money, and then spend something later. So
I would say that the market trend today, and I think especially in the US, is to consider geothermal as a very good renewable solution for those continuous power needs, such as the data centers, for example. So it's kind of the nominated baseload solution for these applications, and this, in my opinion, extremely sensible. And I think with geothermal, we should aim for the maximum possible availability, 99.9% availability. So investment on into a plant that is operable, available, and maintainable with the lowest possible out time, it's extremely important, right?
Yes. It is something that is making your business case, right, business model, to be very, very positive. And of course, to do that, look at to have this availability, as you say, let's say the power plant, it is something that usually has a very high availability. But if we consider the system wells plus plant, now the availability cannot be so high. Why? Because we have to deal with the compressed fluids, right? So
Yeah,
it means
exactly.
that So it means that we need to understand how to do that.
Yeah, to deal with the fluid. Yes. So let's get back to that point, and I think we have a fluid chemistry in the geothermal world that, similarly to what happens to the oil and gas, it's not ideal. It's not pure water. We have a number of components. We have a number of dissolved salts and other minerals. So how can they affect operation, and how to mitigate the problems with silica? So let's start with the typical cases of scaling, for example.
Yeah, I just wanted to show in this slide something that I experienced during some of the commissioning I had. For example, the first picture on the left, it is a piping that was used to produce for well testing. It was in operation for only, let's say, only 12 hours. After 12 hours, those were the conditions. So can you imagine, there was no more sectional area to pass through, and because they were not injecting any inhibitor in the well, because this is calcite. So when you are testing the well, now you are getting what you're dealing with, right? So before that, you can have some rough idea if you have some data coming from other plants, other wells in the nearby, or if you have some, let's say, natural manifestation at the surface, you can have an idea. But until you open a well, you will never know what you have. And especially wells in the same well pad can have completely different behavior. The second picture from the left is a weir box. A weir box is still part of an equipment that it is usually coupled with the atmospheric flush tank that we use for startup and for emergency. What happened here? There was a brine that was high in silica content, and as you see, because of the heat that was coming and the evaporation of the brine in this weir box, the water, let's say, crystallized at the surface like a glass. So that is actually silica. That is glass. The phenomenon was so how can I say, amazing, because a morning I went there and I said, "Hey, what's there? Who put a panel of glass on top of here?" And actually, it was just the silica that was crystallizing there. While the other pictures are, as you can see, problem with the valves. That was during commissioning and operation. The bottom one was calcite. It was a valve that we didn't get why it wasn't closed, so we decided to stop the production. We opened the valve and we found that's what we found. The valve was completely stuck because of the position of calcite. So whatever we were dosing in that moment was not enough to avoid the scaling and the precipitation of the calcite. While the last picture on the right, on top, is just a well that I don't know what happened there. I think they opened it, they did this vertical discharge, and there was some water flowing down, right, from the pipe, and that is the final results of that. So it is very important for us to understand what we are dealing with, because that is what is making our life very difficult. So how we can do that?
So there are a couple, exactly. So there are a couple of ways. There are several ways, but let's say there are a couple of ways to deal, especially with the silica scaling and with the calcite scaling, that are a bit different one to the other. So can you go through that?
Yeah, for sure. As I said, let me say that depending on the brine chemistry, we can understand what is the problem that we are going to face, right? For example, we can know already if we have calcite issue, or if we have silica issues, or if we have sulfides issue, right? So the first way to avoid that, to avoid any issue, of course, is to do nothing with the resource. And you're for sure you know, but that is the case, not the case that we want. So, for example, if you are talking about calcite, we can have downhole injection of inhibitor, where the let's say where the resource is still in the liquid phase. Of course, if you have calcite issues and the reservoir is already a two-phase flow or fluid, of course you have issues because you don't have a level below which you can inject the inhibitor to reduce or avoid, I would say, not to reduce the calcite precipitation, right? So there are also we also need conditions so that the strategies can work. Then for the silica, we can have still inhibitor. These inhibitors could be injected directly at the surface. There's no need to be in the wells unless we have, for example, issues in the well because of silica. I think something like that happened in Alcaria because they have wells that have very, very little water that during the rising up to the surface, they flashes and the silica concentrates a lot in the droplets, and now it will depositate on the surface of the casing, leading to, of course, to obstruct the flow. Or, as I said, we can inject at the surface, or we can use, for example, acidification skids, because especially for the silica, because as defined, it was proven that lowering the pH somehow will help in postponing the deposition of the silica, hoping that once I go back to the reservoir, because of the high temperature of the reservoir now, the silica will be again in condition of not saturation, but will be undersaturated. Then we can also have, let's say, other strategy that is the one of keeping everything under pressure, especially if I have issues with the calcite or if I have issues with something that is related to the flushing, right? For example, if I can pump my fluid and keep it under pressure, for sure I will avoid calcite issues. I will for sure, let's say, reduce the risk of maybe concentration of silica, because sometimes what we need to understand is that if in the reservoir I have a liquid that when it goes up to the surface, it flashes because of the pressure drop and whatever. Of course, the same silica, the silica will be the same, but the liquid will be less. So the silica will be higher in content, right? So this will, of course, lead to some issues. So if I can keep everything in the liquid phase, for sure it will be sometimes it can be useful, even though now I have parasitic loads for the well pumps to deal with, right? So I need a bigger plant because I have also to produce power for this. I mean, we have always to understand what we are dealing with before doing taking a choice, and then of course also the right materials and how I can clean the plant or the pipings is something that we need to keep in mind. For example, in Germany, they're using systems that are kept under pressure, but because of high salinity, the gathering system is usually with a very noble material like the super duplex or the duplex. And I think that something like that is also applies to Salton Sea and in another field in the US. So we need to keep in mind that it's not easy. You cannot say just saying, I have this temperature, I can do this. I mean, you need to be to have more data for that. Yeah.
Clear. So, and sometimes you can only mitigate the scaling, and you need to, or let's say not sometimes. I would say most of the times you can only mitigate. You need to find a trade-off between injecting chemicals, so the cost of injecting chemicals, the period of operations between one cleaning and another. So let's say it's important to design the surface facilities in a way that allows cleaning. I remember one example is that you never use curved tubes in heat exchangers in the binary systems, for example, only straight tubes, but also materials. Sometimes you need to select the right materials in order to allow cleaning, even chemical cleaning, because mechanical cleaning is not always the way. Or let's say talking not about scaling, but about corrosion, you would need some corrosion allowance on your materials.
Yeah,
So
sure.
that's surely a complex a complex solution to a complex problem.
and then you just make me remind that I remember that for example, if I acidify, I can go through the issue of sulfide precipitation because sulfides are driven by low pH. So, I mean, it's always a balance that we need to do to reach the final goal.
Yeah. So let's take a couple of examples of applications of these philosophies for mitigation of scaling.
Mindanao is let's say a bottoming plant in the Philippines, and the operator is EDC. They had this hot brine going to their injection, and they decided to exploit and harness this residual heat that they were, let's say, just let me say waste. They were wasting, but this heat. So they decided to produce more energy, and they found that if they would have gone with a temperature of 90 degrees, they would have issues with the silica. So they decided to implement a silica acidification solution so that we could have, I mean, the outage of the plant should be reduced because now, as we said, we hope that with the acidification, we can postpone the starting of the deposition, right? So this one is, as you said, it's a mitigation, not a full remedial of this kind of problem because it is not impeding the silica to precipitate, it's just avoiding the silica to precipitate a lot. And I think there is also another case study in the US. I think it should be BioWave in Nevada. That is again it's a steam condenser plant, and then there is a bottoming with the binary of the ORC. And again, we have silica there, and to avoid that, the injection of the acid is very important to try to reduce as much as possible the risk of deposition.
Yeah.
I would say
another
that now
example, another example I would say is the one in Nevada for BioWave.
Yes.
Yeah,
for sure.
So
I think we can go
there
to...
are several. Yeah, there are several examples all around the world. Also in Latin America, we work together in the project in Nicaragua where acetic acid was injected, right?
Yes,
so
yes. Also in Berlin, they use this strategy. So New Zealand, I know they use it. So
yeah. So we have a couple of examples, Stefano, before we get to the final section of our conversation of some typical projects around the world. Would you mention some characteristics of these projects, starting from Olkaria in Kenya with the Olkaria 5 project?
The Olkaria 5 project is a 160 megawatt power plant composed of 2 units. And the enthalpy there is very nice because in Kenya, they have this potential and these very high enthalpy reserves. So the reservoir is typically at around 300, 320 degrees Celsius. And they already have a two-phase fluid in the reservoir. They also have a good, let's say, productivity from each well. And more or less, Olkaria 5 had a a range of 30 to 50 tons per hour of steam and 10 to 15 tons per hour of brine. So as you can understand here, the condensing turbine is somehow forced and obliged by these numbers, right? Anyway, they also have a lot of silica, so they also have to separate the two-phase at high pressure just to keep everything hot to avoid any scaling. I know that some studying are ongoing to understand if the brine can be exploited with binary systems. I think the feasibility study is ongoing, and we hope to understand very, very soon what is the results, right? So, and I can see that we also have a similar trend in the US, but the geyser for sure it's like Larderello, right? So we have dry steam and we are all happy about that. But then there is Coso, for example, where we have a two-phase at the surface, and we also have wells that are producing dry steam because if I got well, they just drilled in the steam cap of the reservoir, so the well can produce only steam. So it's, let's say, also here, I would say that because of this high enthalpy, the strategy and the technology of the condensing turbine was the best choice. At least, then COSO is also not a very new field. So also at that time, the technology, the best one was for sure the steam condensing turbine, right? And then COSO is also very, in COSO, they also tried the full injection of the non-condensable gases. And then I think there was some issues because the non-condensable gases were coming back to the production, increasing the content. And now the gas removal system was
undersized.
Was undersized. So they decided not to do that again. So.
Yeah. Great. So we are now at our last section of our conversation that gets a bit more into the synergies between oil and gas and geothermal. And I think before starting this, I would like to take a look at the questions that we got in our chat box. And there is a question that is regarding the use of the oil and gas tools for plant control, and I would say in general for the surface technologies. If you know of any of these specific tools, and let's say I would leave that question on the table while we go through this final part. So first of all, I think it's pretty clear, and it's been very, very much discussed over the last couple of years, how much geothermal can be a natural outcome of the reskilling of the oil and gas professionals in the upstream part. So all the effort done with the enhanced geothermal systems using the shale gas technologies for drilling, for example, is very clear. So let's say the relation between oil and gas skills and let's say geothermal upstream skills is extremely clear. But what about the surface facilities? So how different and how similar are these two words of oil and gas and geothermal?
No, I mean, it's a good question, Luca. It's a good question. I would say that, here in Italy, we are used to unmanned plant. The steam condensing turbine plant are unmanned plant because Enel decided to invest in research and development in terms of prediction tools and prediction software that are now working properly, and they are used a lot. If I can give you a number, I could say that the people that are controlling the power plants, the 34 units in Italy are 3. And then there are people that are doing regular maintenance around the steam field and the power plants. So they build something that can recognize what in Italy is called the signature of the power plant, and if something is going outside of the signature, it will gives you a warning. Hey, something is not going as should be. So go and inspect this. So I think that it's something that it's there also in other application, and I would say that what is completely different compared to the oil and gas are the software, especially for the simulation of the geothermal, because geothermal, like the oil and gas, has two phases. Okay, oil and gas has two phases, also three phases. But what we have here is that we have a flushing fluid, especially with non-condensable gases. So there are several, for example, tools like Olga that they try to that they simulate the behavior of a let's say multi-phase fluid along a pipeline. And there are applications to the geothermal cases, and there are not very good matching because matches because I mean it's completely different field, and there are
Yes.
several issues on that, especially mathematically.
Yeah.
So it's
let's
not
say
so easy.
the skills are similar, but the way you apply them is different, I would
Yeah,
say.
for sure.
Right.
Yes,
So
yes.
the models and the instruments are different for sure. And let's say regarding more specifically the fluids, I think the main difference is that maybe we have less corrosive fluids, but we surely have extreme conditions of temperature and pressure. That's for sure something that makes it a bit harder in geothermal. On another point of view, I would say that geothermal surface facilities, maybe they take more from the power industry than from the oil and gas industry, for the reasons that you just mentioned. So we see the fluid more as a feed than something that we have to deal with in a complex manner, such as in a midstream oil and gas facility, right? So let's say there is another point that I think is worth mentioning, and is the fact that just like oil and gas, what you see on surface is a very frequently an effect of what's happening in the subsurface. And you are both influencing the subsurface, like for the case that you mentioned for COSO with the reinjection of the NCG, and you're getting a feedback from the reservoir. So
for
that's
sure.
another very good similarity of that I think gives a good idea of how interconnected and how multidisciplinary are these two worlds.
But if I may look at what I would like to underline is that actually an oil and gas field will end at the end of the day because it is not rechargeable. But a geothermal field, if you manage that in a good way, it could last for several decades. I mean, that is, I think, the biggest difference that you can have. Then for the rest, I fully agree. Similarities are everywhere. Now it's a matter of understanding where we can, I mean, steal or lend what tools and experience, right, from the oil and gas.
Yeah. So I think thank you, Stefano, for the very good conversation. I would open to even more questions. I think we have another question that just came in regarding the naturally occurring radioactive materials in high enthalpy geothermal fluids. That's something that maybe connects a bit the subsurface and the surface. So the question is, are there naturally occurring radioactive materials in high enthalpy geothermal fluids?
I will change the question. Usually, my knowledge and my experience is in low enthalpy. For example, in Germany, I don't remember now if it is in the Rhine Valley or close to Munich. One of the two places, they have issues with the radioactive materials. So in the filters before the power plant, because as we said, in Germany, they pumped everything, right? They keep everything under pressure in the liquid phase. So they have also filters before the heat exchangers. They have this issue of the radioactive materials. In the other place, sorry, I don't remember now which one was. They don't have this issue. So in the high enthalpy, honestly, I have never experienced that, and I also don't know if anyone is going to do this test about these materials.
Yeah, yeah. So I think there is another point that I wanted to discuss about this. I mean, that is related to these questions on the oil and gas instruments and tools, and the power generation tools, and also the more modern, let's say, machine learning and AI tools. I think we have seen in the past, and you mentioned it when you were talking about the signature curves of the components. I think that geothermal, being just like the oil and gas world, being an extremely capital intensive market, and let's say with an extremely capital intensive business plan, I think it's always extremely important to understand that the operation that will last for 30 years after your development will need to be taken care of also with new instruments. So we are seeing this prediction and let's say predictive maintenance tools going online in many cases, and they've been online in some companies for more than 10 years, maybe 15 years, and they're helping a lot, improving the performance. So I would say that we generally see geothermal as a very conservative word, but all the new technologies that are being applied are extremely interesting and are very positive for our market as well. So we have another question. We see when we see steam rising off a surface facility, does that mean it is water cooled, or we can also see steam from an air cooled facility? I think we need to distinguish where the steam is coming from, right? So in one thing, so in some cases, unfortunately, there are some wells which may erupt or maybe left open, and that's geothermal steam. In some other cases, there may be cooling towers, right, Stefano?
Yeah, I mean, yeah, for sure. I would say that if you don't go for the traditional binary system, right, that use a air-cooled condenser, they also, let's say, discharge to the atmosphere the NCGs with the small steam quantities that we were talking about earlier from the evaporator on top of the so-called ACC, right, air-cooled condenser. So actually, you could also see some steam coming out from the dry cooled facility because of that. So because some steam is still emitted to the atmosphere because of the discharge of the NCGs, and you cannot avoid that steam to be with the NCGs. Of course, if you see, let's say, a wall of fog coming from a facility, it should be most likely we have wet cooling towers.
Yeah, exactly.
Especially in the cold. Remember when you go in during cold temperature, it's like seeing a wall.
Yeah, and I think we also need to be clear that when someone sees a natural draft cooling tower, it's not always a nuclear plant. It can also be some old school huge power plant like the ones we have in Tuscany.
Yeah.
Great. So I think it's been a great conversation, Stefano. I don't know, Deanne, if you want to come in now.
Yes. Let's remind everyone too, to use the QR code on the screen to complete a brief survey about today's presentation. And I just want to thank you, Stefano and Luca, for this very relevant presentation. Thank you, everyone, for your participation, for asking all these great questions. Thank you, everyone. Have a wonderful day.